we're doing absolute, max and min. Now, if you're, let's say you, and I explained it to you last time as well. If you have a graph like this, let's say I'm just making a graph. Can you tell me, I mean, just off topic, this kind of a graph, what degree polynomial this must be? Is this a quadratic? Is it a cubic? Is it a quartic? 5 degree, 6 degree, 7 degree? Just looking at the graph, can you tell me?
Fifth down.
Power 5? The x-intercepts decide what is the degree of a polynomial. When you have a linear polynomial, x plus 2 equals to 0, you get a straight line. It cuts the x-axis at one point. So it's a 1 degree polynomial. Y equals to x square, cuts at 2 points, 2 degree polynomial. So this must be 1, 2, 3, 4, 5. X is for 5. Something with respect to that, right? Commonsensical. Anyway, coming back. What are the mins and maxes here? That's a max. That's another max. That's a minimum point. That's another minimum point. These points are called local max, local max, local min, local min. But then if I look at the maxes, the maximum of the maxes is called the absolute max, which in this case is this point. The highest point of your curve is called the absolute max. And similarly, the minimum point of your graph is called the absolute min, number 1. Alright? At these points, if you draw tangents, the slope of the tangent is 0. That means if you're given a curve and you take the derivative of that curve, equate it to 0, that will start throwing you these maximum min points. Why? Because derivative is the slope of the tangent. And slope of the tangent is 0 across all these points. This is just the concept part of it, right? I've just reiterated it. Any dramas here so far? Any dramas here? Cool. All right, let's now do a question, right? Let's do a question. All right, so it says, the question says that there is a farmer who needs to fence a rectangular farm, right? He needs to fence it, a rectangular farm. The perimeter of the rectangular farm, is 200 meters, right? He says, what are the dimensions that will give him the maximum enclosed area? Max enclosed area. That means he doesn't know what's the length and what's the width. He needs to put this fence in such a way that the area inside here is max. Now, whenever in exams, in SACs, in any evaluation, you see the word max or you see the word min, straight away, first thing that should pop to your mind is you need to find differential of something. Differential has to be taken, and that differential has to be equated to 0. Why? Because we need to find the max or the min. Correct? We just talked about it, right? Now, in that context, if we look at this problem, who can tell me differential of what needs to be 0 here? And you're fine to go wrong and utter wrong. Okay? I'm just reiterating. I need an answer. Differential of what needs to be 0? That's what it is given to me. Perimeter is given and it says, okay, give me the max area. How will you approach this problem? What will you do? Chris?
The area formula, so length times width.
Correct. Dimensions of what? With maximum enclosed area. Maximum area. So you need to use the area formula. It's given in the question then, indirectly. Ayushka, is it making sense? Right?
Yeah.
Now, Ryan, what's the area of a rectangle? Length times width. Yes, Kisha? Length times width? Now, length times width. So now I'm saying I need, let's say area be A equals to length times width. Correct? I need to find the differential of this area and equate it to 0. What is the next step? What will I do next? I figured it out from the question that, all right, area needs to be maxed, so I need to find differential of area equated to 0. Now area's formula is length times width. What next? What's the next step?
You can re-express L in terms of W.
Good job. Any more thoughts? Speak up. Any more thoughts? Right? Isha? Ayushka? It's okay to go wrong. It's okay to go wrong.
The perimeter is 200 meters, so...
We need to do something about it, right?
Yeah.
He's not just giving it for fun.
So
We need to do something like about it.
2 lengths.
Exactly.
2
So
lengths.
let me just say perimeter is what? 2 length plus 2 width. And I say that is nothing but equals to, I like to write on the right, 200. So that's another known thing to me.
So we can solve for the length using that.
Correct. So now the problem here is that you have to find derivative of area, and the derivative of any variable is found with respect to another variable. We said dy by dx, y with respect to x. The problem here is you have 3 variables here. You've got area on the one side, so you know dA by something. So you need to chop these two into one, and then you find the derivative with the area with respect to whatever you've got left here. So length and width. So let's do something so that we have area either with lengths or area either with widths, and that is where this comes into picture. So let's say I decide area, I need to find this dA by dL. So that means everything has to be in L's here. So what do? I can convert my W's into L. So I'll say 2W equals to, that's what Chris said. And then W equals to 100 minus L. And you plug this here and you say your area is L times 100 minus L. So which is 100L minus L square. Now you can easily find dA by dL, equate it to 0, find the value of the length. The length value will be the max length value. So once you've got that, plug this here, probably here, and find width. That is what is required in here. Making sense? 100%? Right? Oh, good. Can you quickly find the length and width, please, for me? I've done half of it now for you, right? Quick. This is 100L. 100L minus L square. Go for it. Quick, quick, quick. So after you solve it, you'll get length equals to 50. Width equals to 50. Chris, yes? Ryan, yes? Kisha, that makes sense? So 100L minus L square. So it's 100 minus 2L equals to 0. L is 50. That's the derivative. And you plug this here, it's another 50. All good? Make sense?
Yeah.
All right. All right. Let's understand double derivative. What is double derivative? Now, what we are trying to find here is, Ryan, f double dash x. That's double derivative. What's single derivative? F dash x. And if the function is f of x. Correct? This is symbolic, how you represent it. Forget about the double derivative for a while. And let's understand how is f of x, the function itself, connected to its derivative. What information the derivative gives me? What information derivative gives me? If I have a graph like this, f of x, this is f of x, and this is x, and I draw another graph which is f dash x to x. So obviously this is negative f dash x, and this is negative f of x. Correct? Now let's say I have a parabola. You remember when we did the derivative graphs, we said, how you derive the derivative graphs from the original function graph. So what was that? Wherever the turning point is, that turning point is basically the same value of turning point here actually becomes the x-intercept of the derivative graph. Remember that? And then we said, okay, this is a negative slope, negative slope, negative slope, and then negative slope becomes 0, and then positive, 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 and so on. What is negative? The slope. What is slope? The derivative is the slope, right? Rate of change. So that means until 0, from the negative infinity, from the negative side of infinity until 0, the graph derivative is negative. It's just like falling. That's the derivative, and that's the negative side of derivative. So it must be from the negative infinity, which could be here, we'll hit here. Yes, it's all negative, it stays underneath. At this point, it is 0. At this point, it is 0. And then from here, it takes off to the positive infinity, you see here. Right? So in this whole story, what is derivative telling me? Where is this function max or min? That's what it's telling me, right? Where is this function? In this case, it is min, right? Because that's the minimum turning point. Where is this function min? Where is this function minimum? Where is f of x minimum? That's what it tells me. So far so good. I haven't talked about the derivative, double derivative yet, but is this clear? Right? Yes? Now let's talk about now I'm just drawing the f dash x now, right? Negative f dash x minus x. What is f dash x? It's called the rate of change, the instantaneous rate of change, or the slope of the tangent of the slope of the tangent at a point on the graph. So so basically the slope. Now let's say your derivative function, your derivative graph was like this. Let's say that was your derivative graph. You had a cubic, and then you found the derivative graph and you found the parabola, right? Derivatives decrease the degrees, right? So here we took a parabola, it became a linear. So in case this would have been a cubic, that's the derivative graph. Now let's take the derivative of derivative. What is this telling me? Now this will tell me where is my rate of change, max or min. The derivative graph told me where is my function max or min. The double derivative graph just tells me where is my rate of change max or min. Makes sense? Or it's hazy?
Makes sense.
Yeah, because original function derivative told you the rate of change, and then when you do exactly the same story, that means you're trying to find the derivative of the derivative. What you're trying to say is, okay, where are the turning points in the derivative graph? Where is the turning point in my derivative graph? The derivative graph will look like this. So if I draw again, I quickly draw this again to connect all the dots now. Let's say I had this cubic. Let's say. What's the derivative graph? This is f of x, and this is x. What are the turning points? That's the turning point, that's the turning point. So that means that's the x-intercept. That means that's the x-intercept. That's the derivative graph, correct? F dash x. Now, positive. So that means positive, positive, 0, negative, 0, positive. So it will be positive, positive, 0, maybe something like this. Right or wrong?
I think the other way.
Oh, sorry, the other way, sorry, my bad. Thank you for your presence of mind. Is this how it is going to be? At times I need to do mistakes so that I know you're alive, right? All good? Now, if I take the double derivative, what would that be? Yeah, something like this. You see, this graph told me what are the turning points of the original function. This graph told me what are the turning points of the derivative function. This graph tells me this is the rate of change of this one. That's the rate of change for this one. Rate of change, or max or min of the rate of change. All good? Make sense? Right? Now, how can the questions come in? How can the questions come in? Let's open up the book. So the question on the screen says, this is example 29. It says you are given a graph. It says assume that the number of bacteria in the nature, so you're given a function, right? N equals to an exponential function. It has sketched the graph of n of t and n dash t. So you can do that, right? No dramas there. Part B of the question. Read the language of the part B of the question. It says find the max rate of increase and decrease. So what is he asking? He's asking you to find the max and the min for rate of change, rate of increase, rate of change, whatever. So when the question tells